Okay, did somebody try this exercise? At least looked at it in the note and understood it? This example I stated last time. Did somebody try this? Looked it up in the book or note, no, in the notes? I think I should switch off this light. Yeah. Any comment? Is there anybody attending the class? Yash, can you hear me?
Yes, sir.
I know you are typically 9-second attendee, so that's why I looked for you. So, did you look it up?
No, sir. I haven't looked it up.
Okay. Did anybody care to look at it?
Sir, did you give in that last time?
Sorry?
Did you give that last time? I mean,
Yeah, I discussed this, just talked about it, and it is posted in Piazza, the note and the pre-recorded, where the
Okay.
solution is also given.
Okay.
Okay, so then tell me how to do it. So this has a twofold degeneracy in this subspace, and this has a non-degenerate subspace. So how do you deal with it? How are you going to do it? How will you approach this problem? Lochan, you want to try? Are you there? Okay, I should not do this exercise. It gets more and more embarrassing. I can see in the screen some names. How about Anirudh? Would you like to tell how you should proceed?
Sir, is E1 the ground state?
Yeah, it could be. That I don't know yet.
Yeah,
E1 need not be less than A2, but it could be. It doesn't matter because we did both, right? Yeah, Anirudh, can you hear me? Okay. Yeah, so can you tell me, can you turn on your mic and tell me?
I didn't go through that lecture yet. So,
Sorry, I'm not hearing. I can't hear.
sir, I didn't go through the problem yet. So,
No, you don't have to go through the problem, but you know degenerate perturbation theory, the theory last time. So I'm working under the assumption that nobody have gone through it. That's okay. But at least you should know the by now that what is degenerate perturbation theory, how to work it out. So will you like to try? Yes, no, I didn't read it, I didn't understand it, I tried, or I didn't even try. All are acceptable answers, but just say something. Okay, it's getting more and more frustrating for me. Okay, let me protect myself by giving you the solution. So first I want to start with this, okay? And this is the non-degenerate part, the easy part, okay? So it should be, and the eigenvectors are very simple. The eigenvectors are 1, 0, 0, 0, 1, 0, 0, 0, 1. It's diagonal already. So this is the normalized eigenvector. So the first correction will be 2h1, 2. So I am calling it 1. This is also 1 because this is degenerate. So I am calling both of them with the same name and calling this 2. Okay. So I should be doing this to current the correction, and that will give me del 2 1 0. So just check that it's just a 2 line. So then the first order correction is vanishing, the non-degenerate. So I want to do the second order correction. So second order correction will be 2 H1 Phy2 . So how will you calculate it? Can somebody try? How are you going to calculate this object, for example? Ashish, you would like to try?
No, sir.
You have no clue.
Yes, sir. Like I joined just now.
No, it doesn't matter. Even if you woke up just now, it is from previous lecture. So how you? So this problem is, this is a H naught. This is a diagonal matrix, and this is a H1. It's a perturbation. Okay. So this del 2 1 is the first correction according to the formula. So these are the eigenvalues E1, E2. It is already diagonal. So these are the eigenvalues, and these are the eigenvectors. So now I want to plug in this, and I want to calculate the correction. First correction turns out to be 0. So then it is just a plug and play thing. So
Yeah.
next correction is I just want to put the. By the way, I'm extremely happy that you are at least there. So at least whatever you say, I'm already happy. So don't get tensed. It doesn't matter if you're saying something wrong, because so far people are not even here and not even are clueless. And so this is a second order formula. So I am asking you how to calculate it. So can you think? Can you at least start to think? I mean, why everyone is so clueless? Yeah. So why don't you try? So tell me, how will you calculate?
Sir, is that the one state will be projected due to Phi2?
Yeah, of course. But how will I calculate this formula Phi2? That is this whole object in circle. So first of all, so what are the two parts in it? So how do I calculate Phi2? What is Phi2?
The operator that removes the projection of the second,
Right.
the
So what it is?
1001.
Okay. Very good. So Phi2 is not phi 0 0. It's the opposite of that. So it is k not equal to 2. It is this object, right? Because if it is everything is Phi2, then it will just project on that. So this is 1 0 0 1 0 0. So this is basically, if you do it, it is 1 1 0, I think. Yeah, just do it. I will not write it. Okay, this is this object. Now, once you write it down, what you have to do in this formula? So now it can act. So this makes the matrix diagonal. This is a diagonalizing factor. So it will act on in E2 minus H naught. It will give you E2 minus E1. And the 2 is 0 0 1. This factor is 0 0 0 0 0 0 a square plus b square. This factor is 0 0 1. Okay. So now you can calculate. This is a single number when you execute this whole thing, because this will give you a column vector. Column vector into row vector is a scalar. So you'll get a square plus b square by E2 minus E1. So this is the second order correction. Everybody followed it so far? How will you do any calculation like that? AD silence. You know, there was a poem, I mean, it reminds me about a poem we studied in, I think, school. It's Listeners. Do anybody know this poem called Listeners by Walter Delamere? Okay, I'll share with you. You will know that why it feels like that. Okay. So now what about the correction in the first order in the degenerate subspace? How will I do that? What is the rule?
That H11 matrix.
Sorry? How will I
It's
calculate the correction?
H111 matrix with L0 or whose contribution.
So we have to solve this equation, right?
Yes.
Right? So what is Q0? So work it out similarly. The Q0 in this subspace will be 1, 1, 0. Yes. So this will be, you can now calculate Q0 H1 Q0, that will turn out to be 0. So that means the first order correction will turn out to be 0. Okay. So this is one example where the degeneracy is not removed in first order. If it is 0, that means the energy levels are still E1. Okay. So then I'll go to second order. Okay. Now I have to solve this eigen equation. Now you can solve it easily. Q naught is this. P naught is 0, 0, 1. Obviously, you can either do it directly in this method, or you can know that P naught plus Q naught is identity. So you plug in the P naught, plug in the H1. Actually, there is no square. Oh no, the square means it's the second order. It's the second order limit. It's not square. It's second order. If you are confused, let me just remove that. Okay. So now plug all these elements, and you will get the following equation. I'm applying all general formula because I don't know it's the ground state or not. It's generic. This times 1. This is just rewriting this. This equation is basically del 1, 1, 0. And this equation is basically this side del 1, 2, and this side is this guy. So all you have to do now is diagonalize this. It's a 3 by 3 matrix which you can diagonalize. The eigenvalues will be, eigenvectors will be actually it is trivial to diagonalize. You can just diagonalize this subspace. You can block diagonalize. So 1 minus. Okay, this is the first order corrected wave function because 0th order is 0, so there is no 0th order term. And the eigenvalues corresponding to this 2 is not squared, this means second order. Okay, now this is the correction. So the actual energy will be E is E1 minus E1, and there are two labels. Actually, you get two eigenvalues like this. So the second will be, no, E2 plus is minus, E2 minus is plus. So E2 minus is plus this whole of same object. So the second level is E2 plus A mod square plus B mod square plus E2 minus E1. And the third one is zero correction, which means the third one you will get this. Okay, I wrote another thing wrong. This is 0, this is minus. So E1, E2, and this 0 means there is no correction. So third one is just whatever it was. So how the problem changed? I think I'll take that. I'll switch to this side of the board. So the original problem had two levels with the two-fold degeneracy E1, E1 and E2. And after you turned on the perturbation, it went to two levels. One remained at E1. Actually, one remained at here. I'm writing like this, assuming that E1 is greater, but it could be lower also. So you will get E1 minus some factor, and this is E2 went up by some factor. So degeneracy is broken, but at second order. At second order, because first order nothing goes away. The degeneracy stays and there is no correction. And we also worked out the corresponding eigenvectors. Okay. Is it clear now? Now can you, did you comprehend? I mean, at least that now you can do any problem of that kind. Any response?
Yes, sir.
What about others, BSMS? Are
I
you
can
following
understand
it?
the procedures,
You understand it?
the procedure, like the algorithm to do it. I didn't understand the concept yet. I'll have to read on my own.
You don't understand what?
The concept, like the derivation of everything.
Okay. But do you understand at least the formula and
Yes, sir.
application? Okay. For derivation, you have to study. You have to spend some time. You cannot listen and understand. Okay. This part is really complicated. There is no way to. It is like if you watch Michael Phelps swimming and you hope that if you are thrown into water you can swim. That won't happen, right? So you will sink. This is like that. So you cannot. There is no way you can understand it. So please spend some time on it. It's not quantum mechanics is not an easy subject. Quantum mechanics 2 is definitely not a subject which you can easily get. You have to spend time on it. So if you have not understood the procedure, you have to sit on it, work through every step, then only you have a shot. And application is actually easy. That is what I said, that and that is the beauty of this formalism. It is so powerful that it gives you a neat and clean formula at the end that any dump can solve. And if you want to be that person, then it's okay. But if you want to be the person who knows the picture, what is going on, then that is what I want you to do. We want to study that whole thing. But it's just multiplying matrices, calculating some eigenvalues and eigenvector. That is it. That is the power of any good formalism. It boils down everything. It dumps down everything to a very easy calculation. Okay. Now, there is one more example in my pre-recorded lecture and in my note. That's actually a very simple example. It's about a harmonic oscillator problem, but that it's a two harmonic oscillator which are which are far apart and they have an electronic charge. So that's why, because of the oscillation, their distance is changing. So the problem is like that. So it's like two dipoles, you can think, and they they are oscillating, and they are they have some electric charge, E plus, E minus, E minus, E plus. So because of oscillation, their distance is changing, so their dipole moment and everything is changing, the energy is changing. So the problem was to how to deal with that using perturbation theory. It's a simple problem, but it's a very interesting and practical problem that appears in many contexts of chemistry and physics. So go through that, I will not go over it. What I'll do some more applications in atomic physics. These applications are actually historically interesting and important because that is how people first landed on a need to do perturbation theory, and first time people appreciated that okay, using perturbation theory you can get really stuff that's close to experiment. Okay, so if it is fine, let me switch the topic to a different set of examples. Note that the main substance is there, what I have already talked about. If you have internalized it, all these things are very easy, very trivial. So make sure you internalize that first before touching this. So I will talk about the central force potential problem. So this is my some central force. So I can call it minus Jd square by R if it is some nucleus with atomic number Z. But hydrogen atom Z is 1. And so it turns out, so historically what happened that people did various experiments, and those they found that there are more and more corrections. In other words, whatever first, actually historically quantum mechanics was developed from spectroscopy, where people looked at the atomic, the energy states of a hydrogen atom or some kind of heavy atom or sodium atom or something, and they found the spectra is discrete. So that discretization was puzzling, that didn't match with any of the classical intuition. So that was more or less people started realizing. That happened around the time of World War I. By the way, this is also an important time to tell you that we are in the middle of we just gone through a pandemic and now we are facing a war. But it is a matter of fact that the maximum development of science happens either during pandemic or during war, which means unless you put a deadline, nobody works, right? That you have seen already. So unless there is a fire, and fire is pandemic, people are dying, or a war, again people are dying, nobody works. So that's an example of that. And most of the development of quantum mechanics, so for example, classical mechanics was developed during a pandemic, that you know already. The quantum mechanics was developed in the context of war, like background of war, not in the context of war. And a lot of development happened for the purpose of atom bomb and etc. So this development was started around 1905 and around 1900. So that, and the spectroscopic, this is near the World War I, all this development was happening, and between these two wars around 1925 the theory came. And then the theory saw that okay, I can predict the discretization, but I cannot match the exact numbers, exact result. So then they started thinking that what might be missing, and one after another, so their development started happening, and people come up with these different kind of corrections, possibly that the picture is not as simple as that. We think, oh, it's like a planetary motion, some nucleus, and around it an electron is moving, and that should be a simple picture like this. But it is not, because there are charged bodies, and there are a lot of other kind of things which we'll see now. And then once that comes, then the problems, we did the whole hydrogen atom problem in the previous semester very neatly. None of this is applicable anymore. So then what to do? So then you have to add those corrections. So let's say some correction terms, and then the problem becomes unsolvable. So then around that, actually the people who first tried to attack this in a very formal way, earlier people was thinking, okay, if it is a discrete spectra, it is something like harmonic oscillator. Then they said, no, this is a charge. Around that Thomson's experiment happened, Rutherford experiment happened. They said, no, there is a charge involved. So then they say, okay, Coulomb spectra, it is a Coulomb system. So then quickly the need of something of that sort was realized. And I think it was first
Interesting question.
oops. It was first Schrodinger and Rayleigh. So this perturbation theory formalism, the basic formalism we learned, most of them were due to Rayleigh Schrodinger. So they developed, and then there are various forms. There are multiple ways to approach this problem. There are this Lippmann Schwinger form, etc. Many others. But Rayleigh Schrodinger is the one which mostly we are learning here. So they approached, they are the first to predict and tried to develop this formalism and predict this spectral line. And they said it's still not coming close, but it's getting better and better. So then people worked out eventually all other fine numbers. And then by then the experiments also improved. The experiment said, okay, it is even finer. So then people went for hyperfine structures. So today we will talk about the fine structures, and that is what is mainly this course is about. And then I will move on to what happens when you turn on a magnetic field, when you turn on electric field, all those things. But the hyperfine structure requires relativistic correction that we will not discuss in this course. So relativistic means full Dirac equation formalism. A bit of that is required here also, but it's still manageable. So the first correction term turned out to be this, e⁴ 8. Actually, there is a nice book. I read that book in Bengali, but you are encouraged to read that book. It's in Bengali, it's called Bishwasghatak, and if you translate it to English, it becomes traitor. So it's a story of how a Russian sympathizer or a Russian guy stole the details of certain aspects of Manhattan Project and gave it to Russia, and that started that was kind of one trigger point of the Cold War, where multiple countries were having atom bomb. And it's a very thrilling story, and the story involves all these characters: Feynman, Oppenheimer, and who else? All these people, Bohr, etc. And all this involving this Germany, America, and Russia. And it's a very thrilling story how all those things happen at the backdrop of when the quantum mechanics was developing, and behind a war was going on where nobody trusts each other, and a very complex scenario and political scenario is underplaying. And around that time Turing also developed his computer and etc. So it's very thrilling. So you're recommended to go through that book. Yeah? It's a story book. It's partly fiction, not entirely history, but it still has a lot of facts. So there is a term called LS coupling, which I'll describe today. So LS coupling is due to the fact that an electron is a moving object, and a moving object generates a magnetic field. And it is not just a moving object, it is a moving object in the electric field of that is created by the proton. So that generates a particular type of magnetic field, and that magnetic field interacts with the spin. Okay. So this term comes because of that. This is called spin orbit coupling, because spin has a magnetic moment and orbital motion generates another magnetic moment. So they are interaction, which we ignored so far. And then there is another term . So this term, this kind I call it relativistic correction. This term is LS coupling. And this is some Darwin term, not the weird biology Darwin, some other Darwin. So, and this Darwin term is a relativistic term. So I will not go in the full details of that. Okay, so let's first talk about this term, relativistic correction. So T means kinetic energy. So kinetic energy will be this, where m is the rest mass of electron. So now if my velocity is small, the velocity of electron is small compared to velocity of light, I can do expansion of this term. Okay. And that expansion will be actually I can do the expansion anyway, but I can terminate it only if it is only if p is small. Okay. So let me keep only terms up to this order, which is p to the power 4 order, assuming that the T of electron is much less than e raised. So this is where I am getting this kinetic term, which is this. Okay. It's a approximation under the, so where I am adding the relativistic correction, but I am throwing away higher order terms. Now this object, this term, so let's estimate what is the small parameter of this expansion, So the small parameter is, as you can see here, is momentum. So if I write the p as mb, so the m square terms will go away, m square m to the power 4 will go away. So the small parameter is v by c. Okay. So this is the small parameter of this. This is my epsilon. So the b by c is e square by h cut c. Do you know why b by c is e square by h cut c? Do you remember this discussion in Bohr's theory, Bohr's atomic theory? Can you guess that how you will derive, even if you don't remember, how can you write down the velocity in terms of electrons charge and Planck constant? Any guess?
Kinetic energy equal to potential energy.
So what kinetic energy and what potential energy?
I mean, when it's moving in a circular orbit about the proton, then it will have, sorry, not kinetic energy, it's mv square by r, the centrifugal force equal to the electromagnetic.
Correct. So it's not kinetic energy, potential energy. It's a balance between centrifugal force and the Coulomb force.
Coulomb force.
And it must be quantized also. The Bohr quantization also should enter. So that should be e square by 4.
MVR equal to, in terms of MVR equal to NH force.
Right. Now this object, have you seen this thing anywhere? This guy? Do you know what this e square by h cut c is called?
Hyperfine structure constant.
Yeah, so not hyperfine.
Fine structure constant.
Yeah. So this is alpha and this is 1 by 137. Why it is called fine structure constant, we'll see it. But the fact that this is a constant and this is a constant of nature, because all the object in it are it's almost 1 by 137. E, h cut and c, all of them are constants. Okay? And this is the small parameter of this problem. And then you can clearly estimate that the relativistic correction term. Now if you see the relativistic correction term, this term, the ERK by E naught is order of alpha square, and that is order of 10 to the power minus 4, because this is order of 1 by 100, 10 to the minus 2, so square is order of 10 to the minus 4. So you can see how fine is this correction. So this is called fine correction. But we will go, actually we will learn in this course, we will learn only fine, but there is hyperfine and then QED corrections. All these things take you together towards the 16th place after decimal. But unless you are measuring energy at that kind of precision, which we can measure in spectroscopy, this correction is not important. That's why we didn't discuss it initially.
So
So my H, yeah,
what is in the denominator of ERK? Is it E0?
E0, yeah.
Yeah.
The term that is coming from, this is my H0. And this is my H1. Okay.
Yeah. Okay.
So right now I'm talking about only this. So this is only my H1, and I'll call other them, bring others one by one. Okay. So now let's apply the perturbation theory. RK. So for time being, let's ignore the spin, because the spin is a separate part. So H RK. Spin has nothing to do with this kind of motions, Coulomb force, rotation, etc. It's an internal degree of freedom, so I'm ignoring it for now. Okay. So let's plug in. This is my original problem, the H naught, the Coulomb problem, which we did in last semester. We found the solution is of 1 by n square, 13.6 eV 1 by n square. If I write it in terms of this, it will be m e to the power 4 by twice h cut square. Okay. So which I can rewrite in terms of the Bohr radius. This is just convenience. If 1 by n square is the most important term, everything else sets the scale. Assuming the z is equal to 1, the hydrogen atom. So now we have to calculate this object. So what is this object? P to the power 4. And everything else is a constant. So let me take them outside. 8 me cube c square. So p to the power 4. How will I calculate an object like p to the power 4? What is the dumb formula? At least tell me that, then I'll tell you a trick.
Ladder operator.
Ladder you can do, but this is linear momentum. This is not angular momentum. This has all the R part and spherical harmonics, everything.
So can we split it into p square and try to like do NLM times p square as one operator and p square times NLM, something like that?
No, but p square once applied, that will still you have to work out the effect of p square. In principle, you can do all this, of course. In principle, you can do the most complicated thing in the world, which means brute force calculation of the full p to the power 4. But in practice, what is useful is to notice this. That's H naught is p square by 2m minus e square by r. That means p square NLM from this formula. This is basically the simple formula. P square NLM is and that is 2m okay. So that is quite easy to calculate, because now the p square calculation boils down to the only non-constant object here is 1 by r. Everything else is a constant. Everything else is coming from the either a constant or coming from this solution you already know. So then ERK1 is basically minus 1 by, so let me write it as proportional, not write this factor again and again, write it as proportional to NLM En minus e square by r right? So now I can expand this. There is still a problem. The problem is this thing is en square minus 2en plus e to the power 4. So now this squaring this object, this angular bracket means expectation value between n and m. So Safi, did you mean this when you said squaring? Safi, can you hear me? Okay. So this squaring, so now here I have to square it, and the square gives me a 1 by r form, which is the only non-constant, and a 1 by r to the power 4 form, okay, when I expand it. So then I have to know how to calculate 1 by r and 1 by r to the power 4. Okay. So let's see, how do I calculate, will there be a 1 by r square also? Let me expand it actually properly. I think I did something, wrote something wrongly in my note. So this is En minus e square by r, En minus e square by r. So this will be En square minus e square by r 2En plus e to the power 4 by r square. Yeah, it should be r square, not r to the power 4. Okay. So I should have to calculate then, and 1 by r expectation value. So let me write it in this side. So the job of calculating p to the power 4 have now reduced to calculating a 1 by r expectation and a 1 by r square expectation. Okay. Now this is relatively easy to handle, but I'm not going to do the calculation. I will tell you how to do it, and you should try to do it. There is again another trick you can do. You can again do it in the dumb way, which means you can write this full NLM, and the LM part is the spherical harmonics that will come out, and the wave function that contains the NL that you can integrate out, and that can simply give you this 1 by r and 1 by r square expectation. It's very simple to do even in dumb way. But then there is another smart way to use something called a Hellman-Feynman theorem. So the theorem is, it sounds like a theorem, but it's actually a very simple assertion that can be proved very easily. That tells you, if you take a state with a parameter lambda, del E del lambda, then the psi lambda, H lambda, psi lambda with the parameter is related like this. Okay. So that means you can calculate an expectation value of the H lambda by calculating simply a derivative. So you can do that actually by using this. So if you write your H E as p square by 2m minus e square by r, where the parameter is E. So then you can plug in the formula del E, E del E. E is the charge is your parameter. So H E psi E. You plug in this, you get the 1 by r here, and the p square by 2m, you can also calculate that. So that will give you the the 1 by r expectation value just by taking a derivative on the energy. So similarly, you can apply this one more step by writing your H as HL. So it is P square by 2m plus L into L plus 1 by r square minus E square by r. So now the parameter is L. So then when you take derivative with respect, in that case, that will give you the energy value with the L, and that will this derivative will allow you to calculate 1 by r square. So try these two things and calculate it also the dumb way. So this is your homework. Calculate it using Feynman-Hellman and calculate using the dumb way and see the matches. Okay. So I'll write down the answer here. So the answer will turn out to be, the m doesn't matter, only the NL, because the spherical harmonics part will not bother because r is only r dependent, not theta pi dependent. You will get z by a naught n square or minus 2en by e square, where a naught is the Bohr radius. Similarly, 1 by r square, you will get it to be 1 by a naught square n cube n plus half. That will give you 4 en square by e to the power 4 n by n plus half. Okay. So when you put all this thing together, your relativistic correction will be minus m this is your first relativistic correction of the order of alpha square. Okay. Because alpha square is your small parameter, not just alpha. Okay. So now I will add the spin orbit interaction. Now I gave you a physical picture that where the spin orbit interaction comes from. It comes from the fact that the electron, so if I see it like that, there is a proton and the electron is moving around and it has some velocity, let's say hydrogen atom. So in the field of this proton, the electron has a velocity. So you know from electrodynamics that in that case, if I write in this unit, certain units, I think CGS units, the magnetic field will be this. And this magnetic field will affect the, so you know Stern-Gerlach experiment and all. You put external magnetic field, the electron experience that. Similarly, here is a magnetic field, but it's internal, not external. It's coming from the system's motion of charge. And then the electron will experience that field because of its spin, and that is this effect. Okay. So it turns out you can write down this as minus mu dot b, and mu is the magnetic moment of the spin and b is this magnetic field. So now do a little bit of algebra, and it's a classical mechanics problem, classical electrodynamics problem, and convince yourself that this object is, it's worked out in my note by the way, mu dot b cross r. It's exercise in classical mechanics, where because of a motion of a exercise in classical electrodynamics, motion of a charge, there is a magnetic field. Motion of a charge in the electric field of the nucleus or proton, there is a magnetic field, and that magnetic field generates, that magnetic field is given by this, if this is the distance r and the velocity is v, and that will couple with the, like earlier you saw this s dot b or mu s dot b in the Stern-Gerlach. Similarly here it will be mu dot b. Okay. So when you do this, when the, so this v cross r is basically the angular momentum, orbital angular momentum. This thing becomes e square by m square c square r cube L dot S. So this is the LS coupling. Okay. So now we will like to calculate this LS coupling. And notice that in the LS coupling form, there is a R cube. So obviously, when you try to calculate this correction between NLM, now you have to determine the 1 by R cube expectation value. Okay. So how will you do such a thing? So think about this. How will you calculate 1 by R cube? How will you calculate 1 by R cube? And I will write down the formula and try to prove this. Okay. So make sure you do these things, because this could be easily the subject matter of next week's these small short quizzes. Make sure you do it and they are well versed. Okay. So we'll take over from there. So we'll take over from there that how to calculate the spin orbit coupling correction, and we will see that it will be similar to this relativistic correction in expression. The functional form will be similar. So and together these two corrections, so let me also write down the together how it looks like, and then we will
So the Hellman-Feynman theorem, like the equation isn't dimensionally consistent.
is what?
The Hellman-Feynman theorem that you wrote, it isn't dimensionally consistent.
Why?
You had
Because one side you have energy derivative with respect to a parameter,
but the
another
parameter had wasn't like we took that to be the electric charge.
So this side also have derivative, that side also have derivative, right?
Oh no, the right hand side did not, right?
Sorry?
The right hand side did not have a derivative.
Oh, didn't I write this? What did I write? Oh, wait. Then I think I wrote it wrong.
Yeah, you missed the dt lambda.
Oh, okay. Good. Okay, good that you check this kind of things. Very good. Okay. It's fine now, right?
Yes, sir.
So this delta E1 is the relativistic, delta E2 is LS coupling. When you do that, you will get alpha square n square 3/4 minus n j plus half. Now there is another term, this Darwin term, which I will not do. So because it's a relativistic, it requires Dirac equation. So this will complete the fine structure. And then there is, so tomorrow in the next class, in Monday, I will talk a little more about this. I didn't do it properly. I just ask you to read, but it is easy enough for you to read. You know all the basics. It's just basic applying it. And this is fine structure. This plus Darwin fine structure. But you can add more relativistic correction. That's called like lamp shift, etc. That requires QED actually, relativistic, and so that is called hyperfine. More higher order corrections. And there is one more catch, conceptual catch, which I want you to think, is that notice that we know that hydrogen atom or this Coulomb interaction energy spectra is degenerate, right? They are marked as some integer n, this n, not here, 1 by n square. They are marked as 1 by n square, but there is a huge amount of degeneracy, which is because of angular momentum and all these things, which we learned extensively. But then why did I apply this non-degenerate perturbation theory kind of formula? I seem to be calculating everything by using the simple naive non-degenerate perturbation theory calculation formula. Think about this. Why did I do that? Is it correct? Or if it is correct, then why it is correct? So I will end the class with this question. And the next class we'll talk about Stark effect and Zeeman effect, where we turn on a magnetic field. I'll talk a little bit about the spin orbit, which I didn't do properly. Then I'll talk about Stark effect and Zeeman effect, and that will roughly conclude this chapter of time independent perturbation theory. Then next week we will do variational method and WKB, and then week after we will move on to time dependent perturbation theory and scattering. These two are really long chapters, time dependent perturbation theory and scattering. So I have to do some time budget such that I can finish the syllabus and teach you some relativistic quantum mechanics also, because that is also part of the syllabus. However, whatever I can complete in the class, that will be that is there anyways, but everything whatever I cannot complete, that will be also there in the pre-recorded form, so you will get everything. Okay. We are running a little behind schedule, so let's see how much we can do. But it's more important, I think, to understand everything rather than completing everything. So let me know where you have to slow down or something. Okay, that's all for today. Any questions?
So the degenerate part, you said there it will be in the Griffiths, but I couldn't find anything in that book.
Sorry, say that once more.
You said that the degenerate part, the first part, I mean the degenerate perturbation theory will be available in the Griffiths book.
Yeah.
But it's not there.
No, I didn't say it is available. It is there in Griffiths, but I am not following Griffiths.
Okay. You're following the
I
Sakurai.
wrote extensively everything what I'm following. I am following Sakurai. I am following
okay.
Sakurai, and this time very closely. It's not like you will find many things which is not from the book. Almost everything I say is from the book, except these physical pictures, the intuition. Everything else is there. I believe it's there. It's not there yet. So that is basically the reference. But I would suggest you to do the following. The best way to read this section is to don't watch the recording videos. I mean, this recording videos has a lot of things. Watch the pre-recorded videos. Then if you feel the need of watching the recording, then you may watch it. But I don't think you will feel. If you have listened the class well, and if you have watched the pre-recorded video with a pen and paper by deriving it, then I think you don't even need to read the book. Even if you feel to read the book after that, you maximum need one quick reading. You don't need to sit down and all. So that is a good strategy to time optimized strategy to internalize this part.
Yeah, thank you, sir.
Yeah, and it will hardly need like 1 and 1.5 hours to go through each video. Videos are all 40 minutes maximum.
No, I mean it's if I do it by deriving all the steps and pausing.
Yeah.
So
So
it is
if you pause it, watch it,
near about
write down,
2 hours.
that will take 1.5 hours. Let's say 1.5 to 2 hours maximum.
Yeah.
So in 2 hours you can internalize an entire. So far I have given how many? I think 4 videos. The first one is just a overall sketchy video. The 4 videos you need each like maximum 1.5 to 2 hours. So that's the best way to internalize this whole perturbation theory. And the problems you don't need that much actually. Problems need even less. Okay.
Yes, sir. Thank you.
Yeah. Stop recording. That's all.